What if I told you that the sky isn't actually blue? What if the very thing you've looked at thousands of times in your life is based on one of nature's most beautiful optical illusions? Today, we're going to shatter everything you thought you knew about why the sky appears blue, and by the end of this video, you'll never look up the same way again. Welcome back to Fact Lab, where we dive deep into the science behind everyday mysteries. I'm your host, and today we're answering one of the most fundamental questions that has puzzled humans for centuries. But before we begin, make sure to hit that subscribe button and ring the notification bell because we're about to embark on a journey through light, atmosphere, and physics that will blow your mind. Let's start with a simple observation. Right now, step outside or look out your window. What color is the sky? Blue, right? But here's where it gets interesting. The sun, which lights up our entire planet, emits what we call white light. If the sun is white, why isn't the sky white too? This question stumped some of the brightest minds in history, from ancient philosophers to Renaissance scientists. The answer lies in something called Rayleigh scattering, named after the British physicist Lord Rayleigh, who first explained this phenomenon in the 1870s. But to understand Rayleigh scattering, we need to take a step back and talk about light itself. Light isn't just one thing, it's actually made up of all the colors of the rainbow. When white light from the sun enters a prism, it breaks apart into red, orange, yellow, green, blue, indigo, and violet. Each of these colors has a different wavelength. Red light has the longest wavelength, about 700 nanometers, while violet light has the shortest, around 380 nanometers. Blue light falls somewhere in between at about 450 nanometers. Now here's the crucial part. When sunlight enters Earth's atmosphere, it collides with tiny gas molecules, primarily nitrogen and oxygen. These molecules are much smaller than the wavelength of light, and when light hits these tiny particles, something fascinating happens. The light gets scattered in all directions. But here's the key, not all colors of light are scattered equally. Shorter wavelengths, the blues and violets, are scattered much more than longer wavelengths like reds and oranges. In fact, blue light is scattered nearly 4 times more than red light. This is why the sky appears blue to our eyes. But wait, you might be thinking, if violet light has an even shorter wavelength than blue, shouldn't the sky be violet? That's a brilliant question, and there are actually 2 reasons why we see blue instead of violet. First, the sun doesn't emit as much violet light as it does blue light. Second, our eyes are much more sensitive to blue light than violet light. So even though some violet light is being scattered, our eyes pick up the blue much more easily. Think of it this way, imagine you're throwing different sized balls at a chain link fence. The smaller balls, representing blue and violet light, are going to bounce off the fence wires much more frequently and in more directions than the larger balls, which represent red and orange light. The larger balls might pass through more easily or bounce less dramatically. This scattering effect is why sunsets and sunrises appear red and orange. When the sun is low on the horizon, its light has to travel through much more of the atmosphere to reach your eyes. By the time the sunlight gets to you, most of the blue light has been scattered away in other directions, leaving behind the reds, oranges, and yellows that create those breathtaking sunset colors. Here's another mind-blowing fact, the sky on other planets would be completely different colors. On Mars, the sky appears butterscotch or reddish-brown because of the iron oxide dust particles in the atmosphere. These particles are much larger than the gas molecules on Earth, so they scatter light differently. On Venus, with its thick, sulfuric acid clouds, the sky would appear orange or yellow. And if you could somehow stand on the surface of Neptune, the sky would be a deep blue, but for entirely different reasons than Earth. But let's get back to Earth and explore some more fascinating aspects of why our sky is blue. Have you ever noticed that the sky appears lighter blue near the horizon and deeper blue when you look straight up? This isn't your imagination. Near the horizon, you're looking through more atmosphere, which means more scattering of all wavelengths of light, not just blue. This additional scattering of other colors dilutes the blue, making it appear lighter. When you look straight up, you're looking through less atmosphere, so the blue appears more intense and pure. The thickness and composition of the atmosphere also affect how blue the sky appears. On a clear day with low humidity, the sky appears a deep, vivid blue. But on hazy or humid days, water vapor and particles in the air scatter light differently, making the sky appear pale or even white. This is because water droplets and larger particles scatter all wavelengths of light more equally, which is called mere scattering, different from the Rayleigh scattering that creates the blue sky. Speaking of water, let's address another common misconception. Some people think the sky is blue because it reflects the color of the oceans. This is completely backward. The ocean appears blue for many of the same reasons the sky appears blue. Water molecules absorb red light more readily than blue light, and the ocean also reflects the blue sky above it. So the ocean is blue partly because the sky is blue, not the other way around. Now, here's something that will really make you appreciate the complexity of this phenomenon. The exact shade of blue we see in the sky is actually the result of multiple factors working together. The sun spectrum, the composition of our atmosphere, the size of the molecules in the air, the angle of the sun, the weather conditions, and even the altitude you're at all play a role in determining that specific blue you see when you look up. At higher altitudes, like on top of a mountain or in an airplane, the sky appears much darker blue, almost purple. This is because there's less atmosphere above you to scatter the light. In fact, if you could somehow remove Earth's atmosphere entirely, the sky would appear black, just like it does in space. Astronauts see a black sky during the day because there are no molecules in the vacuum of space to scatter the sunlight. This brings us to a fascinating point about human perception and evolution. Our ancestors evolved under this blue sky, and it's likely that our vision and even our psychological responses to color have been shaped by this constant presence of blue above us. Studies have shown that looking at blue skies can have a calming effect and may even boost creativity and cognitive performance. But here's where things get really interesting. The blue sky isn't just pretty to look at, it's actually essential for life on Earth. The same atmospheric scattering that creates the blue sky also helps distribute sunlight more evenly across the planet. Without this scattering, we would have harsh, direct sunlight and deep shadows with no transition between them, much like the stark lighting you see in photographs from the moon. The phenomenon of Rayleigh scattering also explains why photographers and filmmakers often prefer the golden hour just after sunrise or before sunset. During these times, the blue light has been scattered away, leaving the warmer, longer wavelengths that create that beautiful, soft light that's so flattering for portraits and landscapes. Let's take a moment to appreciate just how perfect the conditions are for creating our blue sky. If our atmosphere were thicker, the sky might appear white all the time. If it were thinner, we'd see a darker sky even during the day. If the molecules in our atmosphere were significantly larger or smaller, we'd see completely different colors. The blue sky is actually a sign that our planet has just the right kind of atmosphere to support life as we know it. Before we wrap up, I want to challenge you to really observe the sky over the next week. Notice how the color changes throughout the day, from pale blue in the morning to deep blue at midday to the brilliant colors of sunset. Pay attention to how clouds affect the sky's appearance, how humidity changes the color, and how different weather conditions create different shades of blue. You'll start to see the sky not as a simple blue backdrop, but as a constantly changing display of physics in action. So the next time someone asks you why the sky is blue, you can tell them it's because of Rayleigh scattering, the preferential scattering of shorter blue wavelengths by the tiny molecules in our atmosphere. But more than that, you can tell them it's a beautiful reminder of the complex physics happening all around us every moment of every day, turning our atmosphere into a giant natural light show that we're all lucky enough to witness. Thanks for joining me on this journey through the science of our blue sky. If you enjoyed this deep dive into everyday physics, make sure to like this video and subscribe to FactLab for more mind-bending explanations of the world around us. Hit that notification bell so you never miss our latest videos, and let me know in the comments what everyday phenomenon you'd like us to explore next. Until next time, keep looking up and keep questioning everything you see.